Inorganic and organic toxic chemicals in water, sediments, soils, or rocks concern everyone. Most people are seriously concerned with toxins that affect human and environmental health. A major characteristic of toxic geochemicals is that they tend to occur at very low concentrations, many times not being detected or quantified at all by the analytical chemical lab. These non-detected or censored results too often are mishandled by ignoring them or substituting some arbitrary number in their stead. This tutorial teaches you that censored data contain valuable information, and data sets containing them can be described and summarized, compared, and forecast for future desired conditions using statistical models that are technically sound and legally defensible. The consequences of incorrectly analyzed and interpreted toxic metal and organic chemical data include ineffective regulations, denied permit applications, permit holder fines, and litigation. It is important to appreciate the potential for environmental and economic harm, to recognize when geochemical data are incorrectly analyzed, and understand how they should be analyzed. Toxic metals and organic compounds are frequently below analytical method detection limits or censored. Therefore, the three take-home points of this tutorial are: 1. What censored chemical concentration values are and how they are mistreated. 2. How to recognize when censored values are correctly analyzed and incorporated into environmental data analyses, and to reject wrong data analyses. And 3. Why familiarity with these issues is important, especially when the issues involve regulatory actions or litigation. This tutorial will not teach you statistics or ecology. It will teach you how non-detected chemical values should be analyzed in permit applications, compliance reports, and litigation. Censored data are geochemical concentrations that are below the analytical chemical laboratory's method detection limit. That is, the chemical is either not present in the sample or is present in such a small amount that its signal cannot be separated from the background electronic noise of the analytic instrument. Most people know of censored values from medical survival and mechanical failure reports. These are right-censored values because they are larger or longer than the last quantified value. For each chemical constituent, there is a concentration value below which the signal of the concentration is lost in the electronic noise of the equipment. These results are called less thans, or non-detects, or censored because they are below the quantified reporting limit. To illustrate how common it can be for toxins to be absent or almost absent, this list is of metals with 80 to 100% censored analyses of almost 600 samples from streams draining into the Kettle River in northeast Washington state in the vicinity of an underground gold mine. In these streams, there were metals, nutrients, and other chemical constituents of concern that had both quantifiable and censored analytical results. It is quite common for organic compounds such as pesticides, industrial chemicals, and their degradation products to have a similar range of censored observations in analytical reports. There are two wrong ways censored data are interpreted. 1. Ignore them. 2. Substitute an arbitrary value for all of them. Dropping all censored results removes valuable information contained in the original data set. Consider a data set of 100 samples of arsenic collected at a single location on a regular schedule. They will contain some censored values in this set, perhaps as few as 5% or as many as 80%. In CERCLA guidelines, the EPA told data analysts to drop censored values if they constituted 15% or less of the data. Fortunately, demands like this are slowly changing and becoming more realistic. The loss of 15% of data will definitely raise the mean and median values and reduce the variability. When the percentage of censored values is high, dropping them from consideration is a serious mistake because it ignores the knowledge that these chemicals likely have no harmful effects. There are 3 substitutions in EPA, state, and tribal regulations for interpreting censored geochemical data. 1. Replace all with zeros. 2. Replace all with the reporting limit. 3. Replace all with the same value between 0 and the reporting limit. These all are completely arbitrary, have no basis in science or statistics, and distort analytical results by adding information not present in the original data. These also are gradually being replaced with correct methods. The reasons substitutions are wrong are, first, censored values are unknown. Therefore, any substituted value is arbitrary and wrong by definition. Second, there is no scientific, statistical, or mathematical basis for assuming that all these unknown values should be assigned to the same number. Now that you understand how censored geochemical data are incorrectly interpreted, I'll show you how they are correctly incorporated into all the geochemical statistical analyses needed by operators, regulators, and litigators. The first thing an environmental data analyst does with a new data set is describe and summarize the data. This is the basis for determining how to analyze the data for comparing to other data sets, forecasting, correlating, and quantifying cause and effect. Plots are more valuable than tables of data or data summaries because they allow everyone, including non-technical audiences, to see the patterns and important parameters of the data. The most effective illustration is the boxplot, or the box and whisker plot, which is commonly called the boxplot. The boxplot displays the important attributes of the data set that describe and characterize it. The minimum and maximum values, the ends of the whiskers. The range and skewness, the position of the median in the interquartile range box. Any outliers at the extremes of the distribution, as circles beyond the ends of the whiskers. The IQR, or interquartile range, includes the most common 50% of all data and is approximately equivalent to one standard deviation of a normal distribution. The ends of the whiskers are approximately 3 standard deviations from the median, or less than 1% of all values. An example uses a subset of 24 measurements of arsenic in urban streams in the Hawaiian island of Oahu. The first step is examining the distribution of the data using a box plot. It's easily seen that majority of values are well below the Analytical Chemical Laboratory's reporting limit of 2 milligrams per liter. The median value is 0.8 milligrams per liter, and the standard deviation is 0.66 milligrams per liter. While this distribution of concentration values is not unusual for arsenic, Not all metals have concentration distributions as extreme as this one. This figure shows the baseline distribution of our several hundred zinc concentrations in surface and groundwaters of streams in the Kettle River of Washington. Another example illustrates how a box plot clearly communicates the difference in metal concentrations in different data sets. It is apparent that fish liver cadmium concentrations in the Colorado Plateau physiographic region are extremely low, with only about 30% of observations detected, and the median value is about 0.4 milligrams per liter. In the Southern Rocky Mountain physiographic region, 75% of all fish liver cadmium concentrations can be detected. The median value is approximately 4 milligrams per liter, and the same concentration, and some concentrations approach 100 milligrams per liter. Descriptive statistics summarize the data being analyzed by calculating the values displayed in the box plot, including the median or mean, the range, and the variability, the ICR, IQR, the derivative, deviance, or standard deviation. With very small data sets having censored values, generally fewer than 25 total values, this summary is the percentage of censored data, and further analyses use nonparametric methods. Contrary to common perceptions, nonparametric statistical models are scientifically valid and statistically robust. There are 3 types of censored data analytical models, and all produce correct results with small samples. Binary methods for small sample sizes have only 2 values, uncensored and censored. The analysis uses the relative proportions of each to produce useful information. Here is a small data set of 11 values in milligrams per liter. To apply the binary method, the data are recoded as either less than or greater than or equal to the highest reporting limit. For this small data set with its highest reporting limit of 5 milligrams per liter, there are 4 less thans and 7 greater than or equals. The binary method summary is stated this way. 7 of the 11 data values, 64%, are equal to or exceed the concentration of 5 milligrams per liter, that is, they were detected. There is no mean, median, or model computed. Ordinal methods for small sample sizes use the order or ranking of the reported values rather than the values themselves. Tied values each have the averages of their values. These methods can also be used on non-numeric data as long as the values can be ranked. For example, very small, small, moderate, large, very large. Censored values are ranked smaller than uncensored values above the threshold. For the small data set I showed you just before, the ranking is shown here. The ranks of tied values are themselves tied as the median of the ranks they would have had they not been tied. This preserves the sum of the ranks, a statistic used in many nonparametric tests. The 4 values equal to or less than the 5 milligram per liter sum to 10, so the rank for each of the median of 4 or 2.5. Similarly, the 3 values of 8 milligrams per liter are each assigned the median rank 7 in the sequence. Applying an appropriate statistical correlation or regression model for comparison of 2 data sets will yield accurate results without the errors that would result if arbitrary values had been substituted for the censored values. The following analytical methods will use the actual values in the data rather than a characteristic of each value. Maximum likelihood estimates, MLE, assumes that there is a probability distribution that best fits that uncensored values. This makes MLE a parametric statistical model. The quantified values are fit by different probability distributions. The distribution that has the maximum likelihood of accurately describing the data is used to report the parameters of the data, the mean, the median, standard deviation, and so on. MLE models produce poor estimates of samples with fewer than 50 observations. Kaplan-Meier survival analyses are nonparametric because they do not fit the data to a probability distribution to obtain the mean or variance values. Survivorship analysis has been used for decades in medical and industrial studies. Drug and other medical treatments are conducted for a fixed length of time. Cure or other outcome for each patient is recorded. Those waiting for the desired effect when the study ends are recorded as censored. That is, the cure or occurrence time is unknown. Industrial applications determine the time to failure, usually reported as the mean time between failure, or MTBF. In both of these applications of survival analysis, the unknown quantities are at the right side of the survival curve. That is, they are right-censored data. Geochemical data are the mirror image, as the unknown values are on the left side of the distribution curve. Therefore, they are left-censored data. To apply the KM model to environmental geochemical chemistry requires transforming the raw data from left to right censored by flipping the data set. The flipped data now fulfill the requirements of the statistical models and the results of a plot of the probability of observing each concentration in the range of the data set along with 95% confidence intervals. The KM survival model of the Oahu stream's arsenic values is shown in this figure. And these are the calculated summary statistics for these arsenic concentrations in milligrams per liter. Each of the models I've described and others produce summary statistics that differ slightly in numeric value. The differences in median, mean, and standard deviation calculated by each model is, in practical terms, meaningless, because natural ecosystems, particularly aquatic ones, are highly variable. In my experience, the Kaplan-Meier survival model most easily and effectively communicates with finders of fact and other decision makers. Environmental chemical data are often summed, most frequently by adding monthly quantities to calculate the annual amount of a pollutant or contaminant discharged. These estimates add water constituent quantities for which each has the same weight of importance, so the addition is straightforward. It is more complicated summation when each constituent has a different importance weight to be added to calculate the total. This is the case with ecological risk assessments at Superfund sites under CERCLR in accordance with EPA guidelines. The purpose of an ecological risk assessment is to calculate an overall numeric measure of the effects of chemicals such as dioxins, furans, PCBs, and heavy metals on plants and animals. Each of these organic pollutants is a class of similar chemicals rather than a single chemical, and each specific chemical, called a congener, has a different toxicity to different organisms. Summarizing the general toxicity of all congeners in the class on an organism assumes that an individual congener toxicities are added and allows calculation of a toxicity equivalent concentration. One application of TECs is setting recommendations for fish consumption by people. This means that how TECs are calculated can have significant ecological and economic effects. Because each dioxin, furan, and biphenyl congener has a different toxicity to organisms, each congener's toxicity is related to what is accepted as the most toxic, 2,3,7,8 toxichlorodibenzoparadioxin, or TCDD. This is done using a toxicity equivalent weighting factor, a TEF, determined by a group of experts for each class of organisms. TCDD has a toxicity equivalent weighting factor of 1, while less toxic congeners have TEFs closer to 0. The concentration of each congener in the medium, water, sediments, or soils, is multiplied by its TEF to obtain the TEC for that congener. The individual TECs are added to calculate the overall TEC. It is common for a congener's concentration to be below the analytical chemical laboratory's reporting limit. So how these censored concentration values are included makes a big difference in the value of the overall TEC. The only recommendation the EPA offers on the subject is to substitute both 0 and the reporting limit to calculate the range of possible concentration values. You now know that substitution of any arbitrary value for censored values is wrong, and it's unnecessary because there is a simple process to avoid it with censored values in the data set. The sum and the mean are related. The mean is the sum divided by the number of values added. To calculate the overall TEC, multiply the mean concentration of congeners by the number of congeners to obtain the sum. This avoids substitution of arbitrary values, reporting the extremes of a range in which the actual TEC would be found, and is supported by robust mathematics. Comparing two groups is a frequent requirement under all environmental regulations. Are there differences between baseline and operational periods? Are there differences between sites in the same or different areas? Has a remedial action changed the concentrations of chemicals of concern? In some cases, testing is done in only one direction because one group is expected to be either better or worse than the other group. These comparisons use a one-sided test. In other cases, there is no a priori expectation of a difference, so the comparison uses a two-sided test. With no censored values in either set, comparisons use the two-sample parametric t-test or the nonparametric Mann-Whitney test. When either or both data sets contain censored data, options include binary methods, ordinal nonparametric methods, and both parametric and nonparametric survival analysis methods as previously described. It's not unusual to have only a few geochemical concentration values when information must be provided to a regulator or other stakeholder. Despite the paucity of available data, decisions must be made based on this limited amount of information. Earlier in this tutorial, a set of 11 values was separated into two categories: those less than the highest reporting limit and those equal to or greater than the reporting limit. Excuse me. Adding a second small data set allows comparing the two using binary and ordinal methods. The first data set has the highest reporting limit of 5. The second data set has 12 observations and the same highest reporting level of 5. The question is whether these two data sets are significantly different. The percentage of quantified values above the highest reporting limit in two or more groups can be tested to determine whether they are the same or significantly different. The second data set has 3 out of 12 uncensored observations. Is 25% significantly different from 64% with these two sets of data? The test of proportionality results in the probability equals 0.85, much greater than the standard of p equals 0.05. Therefore, the null hypothesis that the two sets are the same cannot be rejected. It seems counterintuitive that two sets of data that appear so different are not significantly statistically different. This is why correctly incorporating censored geochemical data can make a major difference in environmental policy, regulation, and litigation. The same approach can be used to test proportions in 3 or more groups. When all censored values are ranked lower than the uncensored values, a single reporting limit, and considered to be tied in rank, you can directly apply the Mann-Whitney test. This is the nonparametric equivalent of the parametric t-test for two samples. Using ranked order is one step above using binary comparisons based on less than and greater than or equal tests. The first step is to jointly rank the two data sets. Using the previous two data sets, the 23 values have these ranks. All 13 observations below 5 are ranked as tied, and it's assigned the same rank 7, the median of 1 to 13. The uncensored values are also ranked individually, except for ties. The Mann-Whitney test sums the ranks in one data set. If the sum is unexpectedly low or high, the null hypothesis that the groups are the same is rejected. If the sum of the data sets is moderate, a function of the size of the set, the null hypothesis is not rejected. Failing to reject the null hypothesis that the two samples are the same does not mean accepting that they are the same. While the difference might seem subtle or trivial, it is meaningful and one of the drawbacks of this statistical paradigm. The Mann-Whitney test produces a probability, a p-value, of 0.052 after correcting for ties, so the null hypothesis that the groups are the same cannot be rejected. This approach is technically sound and legally defensible. While substituting arbitrary values for the censored data, then applying a parametric t-test will produce results depending upon the substitution value chosen. The use of uncensored values and the proportion of censored observations to calculate summary statistics was described earlier. The parametric MLE can be used to determine whether the two data sets are the same. In the late 1980s, 113 groundwater samples were collected from 2 areas in the San Joaquin Valley of California, 69 from the alluvial fan, and 49 from the basin trough. Both chemicals had censored observations, 31% for copper, 27%, and 20% for zinc, 17%. And this box plot shows the zinc concentrations. One question was whether there was statistically significant difference in zinc concentrations between the 2 areas. A maximum likelihood estimation method tested the null hypothesis that the mean value of concentrations in both areas was the same. The frequentist paradigm for hypothesis testing can only reject the null hypothesis with a probability of less than 0.05. The analysis calculated probability equals 0.94. Therefore, the mean value of the 2 areas is not significantly different, despite appearance in the box plot. There are many situations when geochemical data from 3 or more locations or times need to be compared. Regulators or others might ask whether the means, medians, or the probability of observing a detected concentration of a chemical is the same for all groups, or if there are differences, which groups differ. It is common for the chemicals of interest to be below several laboratory reporting limits, which makes how they are analyzed very important. When all data are uncensored, comparisons among the group is done with the parametric analysis of variance, ANOVA, or the equivalent nonparametric Kruskal-Wallis test. In the usual situation where censored toxin values are found in all data sets, the same methods described in the previous section can be extended to include more groups. Differences among group means can be identified using parametric maximum likelihood methods and the nonparametric Mann-Whitney test. In these situations, not correctly incorporating censored data in the analyses would result in ineffective policy decisions, in regulatory fines, and unnecessary and expensive correction actions or environmental litigation. A multiple group example. This example uses concentrations of trichloroethylene, TCE, in shallow groundwaters of Long Island, New York. Water samples were obtained from wells in areas of 3 residential housing densities, low, medium, and high. TCE levels were expected in each residential area because the chemical had been used in the past as a septic system cleaner and as a solvent in residential and light industrial uses. Water samples were sent to different laboratories for analyses, and over the course of the study, analytical precision improved, so 4 different reporting limits are in the 3 data sets, 1, 2, 4, and 5 milligrams per liter. This figure shows the observations of the residential areas using histograms. Notice the majority of concentrations are very low in all areas, and there were censored values in each area too, so this figure is not very informative. It is important to know that 78.5% of the observations in all 3 areas were censored. Their distribution by density category is more easily seen in a box plot figure. Note that all observations in the low residential density areas are censored. In the medium and high residential density areas, quantified concentrations, those above 5 milligrams per liter reporting limit, are small proportions of all data. This suggests that there might be differences among the 3 densities. If the data analyst ignores the high percentages of censored values by substituting the reporting limit of 5 milligrams per liter, an analysis of variance, ANOVA test, for differences in the means yields a probability of 0.547, and this value means that about 55% of the time these results are expected, and the null hypothesis of equal means cannot be rejected. This bias of artificially high means for all groups introduces a pattern that does not exist in the data and distorts the results. The nonparametric equivalent of the ANOVA test is the Kruskal-Wallis test. Because the question asked of these data is whether the TCE concentrations are similar in the three residential housing densities, the data will be recoded so that all censored values have the same rank, for example, -1, for an overall test of differences. When the Kruskal-Wallis rank sum test is applied to the three data sets without substituting an arbitrary value for the censored values, the resulting probability is 0.01 corrected for ties. Because 0.01 is much less than the 0.05 null hypothesis that these waters are the same is rejected. Going one step further, determining one or more area is different from the others is accomplished using a maximum likelihood estimation to compute a censored regression. This agrees with the Kruskal-Wallis test, as the resulting probabilities are 0.007 and 0.003 for the low and medium density sites. Therefore, all three densities are significantly different from each other, as shown in the box plot of the three areas. Quantifying that each residential area has a different level of TCE in the shallow groundwaters is certainly valuable information for inferring policy and regulatory decisions that would have been missed if the very high percentage of censored values had been lumped as all having this value of 5 milligrams per liter reporting limit. Correlations are associations between variables, not cause and effect. The correlation strength is measured by a correlation coefficient in the range of -1, one variable increases when the other decreases, to +1, both variables change in the same direction. When there is no relationship between the two variables, the correlation coefficient is 0. Correlations are, or should be, commonly used when making and monitoring compliance with environmental laws and regulations. These analyses are particularly valuable when seeking trends in chemical and biological observations over time and space. It may be necessary to remove seasonal effects, spatial autocorrelation, and other factors when processing the data to determine consistent increase or decrease of the variable over time or place. There are three correlation coefficients used in ecology and environmental science: Pearson's R, Spearman's Rho, and Kendall's Tau. Pearson's R is the traditional parametric correlation coefficient commonly used in environmental technical reports prepared by consultants and agency staff. The three quantities needed to calculate this correlation coefficient are difficult to obtain from environmental data, so it shouldn't be used in this context. Spearman's Rho is a nonparametric correlation coefficient, calculating using ranks rather than the actual values. When there is a single reporting limit and ranks can be unequivocally computed, this correlation coefficient is acceptable. However, multiple reporting limits are very common in geochemical data, and ranking values such as less than 1, a detected 3, and less than 5 is subjective, so Spearman's rule should be used only when data sets have only a single reporting limit. Kendall's tau is also a nonparametric correlation coefficient that is commonly applied to trends and can be used with censored data. It is computed by comparing conforming pairs of XY data, that is, they move in the same direction, with nonconforming pairs of XY data, those moving in opposite directions. Kendall's tau can be used with data containing multiple reporting limits. Correlation coefficients can be computed using a contingency table with binomial data when values are coded by assigning 0 to all censored values and 1 to all uncensored values. The test is whether the frequency of detection changes from one group to another. To compute the binomial correlation coefficient phi, the variables x and y is each classified as low or high. There are 4 combinations of these two categories, as shown in the table. The correlation coefficient will have the highest positive value when both variables are high or both are low, and the largest negative value when each variable is in a different category. To illustrate the method, a subset of concentration of the herbicide atrazine in groundwaters is used to prepare a contingency table that is then analyzed using the proportionality test. This table displays the counts of pairs of low values, less than 0.01, and high values, detected or greater than and equal 0.01, for the atrazine data. For these data, the correlation coefficient is calculated to be 0.61. Whether this is significant depends on the question being asked. If the question is whether only a positive correlation exists between June and September, the probability is 0.027, and the answer is there is a positive correlation between the 2 months. If both positive and negative correlations are of interest, the probability is 0.54. Then there are also correlation methods for data using Ordinal and MLE methods for singular or multiple censored data. Regression methods examine the relationship between response variables and explanatory variables. That is, they quantify cause and effect relationships. Regression models of environmental data analyses under the CWA, ESA, NEPA, and other laws provide insights that inform policy and regulatory decisions. Linear regressions are very familiar. They have a line through data which represents the mean value of a response variable on the y-axis to the value of the explanatory variable on the x-axis. Rarely, if at all, can untransformed geochemical data be correctly fit by a linear regression model. When there are censored values in the data set, the parametric linear regression does not produce correct answers. There is a robust nonparametric analog to the parametric linear regression model that can be used with censored data, and it is recommended for use with all environmental geochemical data. The method is the Thiel-Sen regression. The slope is estimated by the nonparametric Kendall's tau correlation coefficient. This line is a linear median, not mean, and is not influenced by outlying observations. The significance test for Thiel-Sen slope is the same as the significance test for Kendall's tau. When the explanatory variable on the x-axis is time, the significance test of the Thiel-Sen slope tests for a temporal trend. As with previous sections, there are other regression methods suitable for censored data in binomial and MLE formats. If there are censored values in both the response on the y-axis and explanatory on the x-axis variables, the Thiel-Sen line is the preferred method to apply to the data. For binomial data, logistic regression models are appropriate. I have presented a categorical approach to determine if there were differences in Long Island groundwater TCE concentrations in 3 density categories of residential housing. Now the question to be answered is the probability of detecting TCE in shallow groundwaters, the response variable, using population density and or depth to the water table as explanatory variables. A maximum likelihood ratio test applied to the population density and water table depth determined the 2 factors significantly affect the probabilities of TCE concentration being uncensored. The results of binary logistic regression is that water table depth does not significantly determine TCE concentrations and has a probability of 0.44. But probability density does significantly affect the levels of TCE in shallow groundwater with a probability of 0.002. There are other regression and trend models that are robust and produce technically sound and legally defensible forecasts to environmental effects of geochemistry. In summary, some scientists have suggested that censored observations carry no information. Therefore, they contribute nothing or little to analyses of the data. This is an incorrect assumption. From a strictly non-technical perspective, the higher percentage of censored values in the data set, the less likely adverse impacts will occur. Using data such as the zinc concentrations from the San Joaquin Valley alluvial fan zone groundwater, a series of analyses with different percentages of uncensored observations found that increasing the percentage of censored values, such as by changing everything 10 milligrams per liter to less than 10 milligrams per liter, strengthened the information signal in the data and produced a lower probability value. This result rejected the null hypothesis that the 2 zones did not have different mean concentrations, even though the alluvial fan data now had a higher percentage of uncensored values than did the basin trough area. Several regulatory guidance documents, including some from the EPA, recommend that statistical tests not be run on data sets with a high percentage of censored values. There is little justification in the statistical literature for such recommendations, as statisticians continue to improve the models. Statistical models that efficiently extract information from censored data, such as the Kruskal-Wallis test, the multi-group equivalent of the Mann-Whitney test, use the information contained in the censored values in the data. There is no reason to limit use of these tools to inform environmental policy, regulatory decisions, and litigation outcomes. You are not ecologists or environmental data analysts, but you rely on correct statistical analyses of geochemical data and interpretation of the results based on established statistical and ecological theories. Therefore, it's essential for you to recognize when censored values are mishandled with resulting distorted and incorrect results. Regardless of the setting, pre-application planning, permit application preparation, permit compliance issues with regulators and others, or litigation, understanding the issues involved with censored geochemical data is critical. Knowing there are robust and valid approaches to analyze censored geochemical data makes you a better informed consumer of reports prepared by technical consultants, regulators, and resource agency staff. When how environmental data are analyzed and interpreted must be technically sound and legally defensible, contact me.